Hello, welcome to today's lecture. Now we'll begin by reviewing some of the points we've discussed in previous lectures and then add some new information and examples related to the fate and transport of toxicants in our environment. Now you've seen this slide several times before, and I'd like to take a few moments to briefly go over the finer points for your consideration. Toxicants and contaminants enter the environment through a variety of pathways. They can enter as waste products from manufacturing. So here we have waste products from manufacturing right here. They can enter as spills in the water or on the land. So here we have spills. They can enter as waste from agricultural operations. Here we have cattle and hog operations, or from human existence or human presence, such as sewage treatment systems or septic tanks. They can also be purposely applied or placed into the environment, such as pesticides in farming operations. Whichever pathway they use to enter the environment, we know that in most instances they don't necessarily stay where they're first placed. Most contaminants and toxicants move about their environment and indeed may traverse anywhere from a few centimeters to great distances, sometimes even crossing continents. We also know that during their travels, many compounds will change their form, which may or may not change where they move and even how fast they move. Now, to simplify all of this madness from the previous slide, we can write this diagram in a very simple form. Toxicants entering an environment can enter or can be found in the air, in the water, or in the soil. And they can move between these compartments. And by the way, each of these areas, the air, the water, or soil, is referred to as a compartment in a whole. And this just refers to the area in which you're discussing the presence of contaminants. Now, as we see in this photo here, toxicants can be carried via the wind. Here I used the dust storms off of the Sahara Desert to illustrate the capacity of wind to carry compounds. So you see it's carrying, where's my little arrow? It's carrying the dust off of the Sahara and across the Atlantic and eventually into the Caribbean and the southern United States. The wind can take materials that are light enough or volatile enough and transport them across vast distances. Based on environmental conditions, these compounds can then move into the water or into the soil of both compartments. So if we wanted to see water compartments, if a contaminant is in the water, I'm not sure you can see this very well, but this represents the movement of water flow around the Atlantic, both the North and the Southern Atlantic Ocean. So here, briefly, you can see the Gulf Stream, the Northern Gyre, the Transoceanic Gyre here in this area. We have the Southern Ocean, or not Southern Pacific, Southern Atlantic here with this gyre. So if a contaminant gets in here, it can travel this way and end up in jolly old England, just based on its movement in these water currents. And indeed, movement via the air or the water is thought to be one of the mechanisms by which contaminants are carried to the Arctic. And then you also have contaminants in the soil. If you look here in this photo, you see different layers of the soil. We have the grassy organic layer up here, the richer areas, and then as you go down, you see the more sediment layers that are present, and you see how they change over time. So these are the older sediments down here, and we have the newer sediments up here. And contaminants can be laid down at each of these different areas, and we're going to discuss that a little later as we go along. But most of our discussion today will concentrate on the latter two compartments, on the water, keep losing my arrow, on the water and the soil. But to understand why and how, we must first understand something about the compounds in question. When attempting to understand the behavior of a toxicant in the environment, there are specific properties that must be known. The first of these are the physiochemical properties. The physiochemical properties. These include the water solubility of the compound. Now remember, most environmental toxicants are hydrophobic, having solubilities in the part per million or part per billion range. But their solubility will be influenced by the pH of the water, whether or not salts are present or not, whether or not there's inorganic materials such as metals present, and also what is the temperature of the water. A large number of compounds are more soluble at warmer temperatures than at colder temperatures. Next, we have to be aware of the composition of the soils. This will influence the absorption of the compound onto soil particles. It is important to know whether the soils contain clay minerals, which can differ in their physical structure. In other words, Georgia clay versus North Carolina clay, even though they're very similar. And their swelling ability. So for the clay materials, it can differ based on their physical structure, their swelling ability, and whether or not cations are available for exchange. Now these cations may include sodium, phosphate, or calcium. And importantly, they also, of these clay particles, the surface area of the clay particles is quite important. High specific surface is associated with a small particle size, and therefore the colloidal fraction is very important. Hence one of the bases for much of the nanotechnologies as far as high surface area goes. It is also important to understand the type and concentration of organic matter that is present in the soil. The organic matter content of most soils usually ranges from 0.1 to around 7%. So most soils have a very low organic content. And this organic content can include both non-humic substances, which are fresh or incompletely decomposed plant and animal matter, and they could contain humic substances, which are more or less completely altered or resynthesized materials, so they've been totally broken down. You also need to consider the vapor pressure of the compound that you're working with, in other words, how volatile it is, the pKa, keep losing my arrows, the pKa of the ionic species, which is the logarithmic measure of the acid dissociation constant, and it relates to its behavior in aqueous solutions, as well as the stability, the chemical stability of the chemical, or how easily it is broken down into its constituent parts. Now lastly, we have to be aware of the partitioning behavior of the toxicant. This relates to whether the toxicant in question exists in the air, the soil, the water, or in biologics. Now the interesting part about this is that all of these different factors can be described using a series of simple equations, and we'll go over some of these briefly in just a few minutes. Now besides the physiochemical factors, there are system processes that must be considered when discussing the movement of toxicants through our environment. This includes whether or not the sediment, if the toxicant is bound to it, moves via the air, such as the dust from the Sahara, or is it carried along with suspended particles within the water. Thus we also have to consider the hydrologic cycle. Is it an arid environment? Is this toxicant occurring in an arid environment? Does it rain frequently? Are there numerous floods? Where and how does the groundwater flow? And if there are aquifers present, where do they flow? We also need to be aware of the presence of microorganisms. This could be different species of bacteria or fungi residing in the soil or the water. Do they degrade the material? Do they feed on the material? Do they change the presence of the toxicant by metabolizing the toxicant? Remember, they have phase 1 and phase 2 enzymes as well. Next, we have the dilution of the compound in the air or water. If the toxicant is readily vaporized, then it could easily move from the soil into the air, or if readily solubilized, could move from the soil into the water, depending upon its hydrology, of course, and the availability of water. This movement or dilution in air or water is some of the basis for some soil environmental remediation, where they're blowing warm air into the sediments and it's volatilizing the compounds up into the air to get them out of the sediments. So you're not necessarily getting rid of them, you're just changing their compartment. You're changing them from the soil to the air. And lastly, we need to consider the deposition of the toxicant into the ultimate sink, or at least what used to be thought of as the ultimate sink, which is the deep ocean. And now, when this is usually considered an ultimate sink, because once materials enter this compartment, the deep ocean that is, they are no longer considered to be available for anything or anyone, because after all, everything moves downhill. However, they're finding that with the migration of many species and the discovery of species in some of these deep ocean areas, that these toxicants may not be at the end-all be-all last place they'll ever occur. That it's possible that they're getting back into the circulatory system of the earth, so to speak. Now, before we move along, I'd like to briefly talk with you excuse me, about how we determine where compounds move through the environment. And to do that, we need to look at some of the mathematical equations used to describe these processes. Now, the polarity of a compound plays a major role in the mobility of that compound. Polar substances tend to dissolve more readily in water than nonpolar substances, and therefore they will absorb soil particles less than the other ones. Now, if a toxicant strongly adheres to the components within the soil, then we can describe this relationship using the equation for the soil sorption coefficient, or the KD. This is where we measure the concentration of the compound in the soil and divide that by the concentration of the compound in the water. So the higher the KD, the greater the affinity of the toxicant for the soil. The lower the KD, the less affinity that toxicant has for the soil. Now, this is directly related to the surface area of the soil and the amount of the organic matter present. Now, this leads to our next equation, where we determine the soil sorption constant, or KOC, which is our dissociation constant, KD, or soil sorption coefficient, divided by our percent organic carbon that is present in that soil. This then gives us an idea of the absorption to the organic matter fraction of the soil. Remember, the soil will be made up of inorganic particles and organic particles. And so this equation will tell us how much of our contaminant is bound to the organic fraction of that soil. And this will be dependent upon the physiochemical factors that we discussed earlier. Now, next, based on vapor pressure and the solubility of the toxicant, we can calculate the air-water ratio, or KW, by determining the concentration in the water versus the concentration in the surrounding air. This will tell us the propensity for the chemical to volatilize, thus moving from the water into the air. So if we have a low number, it's very volatile. If it's a high number, it's not. Now, if we wish to determine the KOW, or octanol water partition coefficient, which is just a simple measure of the hydrophobicity or water repulsing activity of an organic compound. Now, the more hydrophobic a compound is, the less soluble it is. Therefore, the more likely it will absorb to soil particles. KOW can be determined by adding a known amount of contaminant to a bottle consisting of equal volumes of octanol, which is a chemical solvent, and water. So you have octanol and water in a bottle. You add a known volume or a known amount of contaminant. You shake it up, separate the two phases because octanol and water won't mix, but the contaminant will go into either the octanol or the water phase. And then you take it out and you measure each phase. And the coefficient is determined by calculating the concentration in the octanol phase compared to the concentration in the water phase. And so that will tell you how hydrophobic the compound is. And lastly, we have the movement of toxicants between the water and the biota, which here is determined as fish, but it could be any aquatic organism. Now this is known as the bioconcentration factor, or BCF. This is calculated by determining the amount of toxicant within the organism and comparing it to the concentration within the water. This information provides relative ranking of chemicals, although variations will occur among different organisms, especially with respect to the bioconcentration. And this is most often due to the lipid content and lipid composition of an organism's tissues. In other words, the fat or lipids that are present, say, in a oyster tissue compared to blubber of a dolphin or something of that nature. So it'll vary based on that. So to summarize these relationships, we observe that contaminants can move from the air to the water and then into the soil, and that the rate at which this occurs or the strength of the affinity can be compared between toxicants by comparing the Kw or the KOC. So we can compare how rapidly and how likely these contaminants would move from air to water to soil. Okay? We can also see that toxicants can move from the sediment into the water and possibly into organisms living in the water. Now these relationships can be described by comparing the KOC and the BCF. So I hope you all understand that. Whether or not it's moving from the air, the water, to the soil, or from the sediment to the water to the living organism. Now remember the pesticides we discussed previously? If you recall, each of these compounds will differ based on their toxicity, stability, solubility, and absorptivity. If we examine just one of these, and let's look at chlorpyrifos, otherwise known as Dursban, we can see that the movement of it within the environment. Dursban or chlorpyrifos is a broad-spectrum insecticide that is effective in controlling a variety of insects, including cutworms, corn rootworms, cockroaches, grubs, flea beetles, flies, termites, fire ants, and lice. It is used as an insecticide on grain, cotton, fruit, nuts, and vegetable crops. It's also used on lawns and ornamental plants. It is also registered for use on sheep and turkeys, for the treatment of horse sites, such as barns and feedlots, for the treatment of dog kennels, and for domestic dwellings, farm buildings, storage bins, and commercial establishments. Basically, it can be used almost anywhere. Now, chlorpyrifos is one of the class of insecticides referred to as organophosphates. You see it has a phosphate group within its structure here. So this is an organic phosphate, and these chemicals act by interfering with the activities of cholinesterase, which is an enzyme that is essential for the proper working of the nervous system of both humans and insects. Now, chlorpyrifos absorbs strongly to soil particles, and it is not readily soluble in water. It is therefore considered immobile in soils and unlikely to leach or to contaminate groundwater. Its solubility in water is 2 parts per million. It has a KOW of 66,000 at 23 degrees centigrade. It has a KOC, where'd my arrow go again? It has a KOC of 7,000 to 25,000 mils per gram, and it has a KD of 128,000. So therefore it's reasonable, given all of these parameters, that we would see higher levels of this in the sediments of a river, as shown here, than in the water itself. And this is data taken, I think, from the Neuse, but I won't swear to it. It may be the Pamlico. And as you see, there's higher concentrations within the sediments in that river than within the water of that river over a certain time period. Now let's move on to a different example of contaminants within North Carolina. North Carolina is home to numerous hog farms, as shown in this graphic taken from the North Carolina Department of Agricultural website. And if any of you have ever driven from Morehead City, which is located right here, to Raleigh, you go through a lot of hog country. Now, as you can see, the majority of our hog sites occur in eastern North Carolina. So if you take this little swatch right up through here, those are the major hog operations. And you may see them if you've ever flown over eastern North Carolina. This is what they look like. A lot of these times, these retention ponds here are hot pink. So you might see those, and that's just due to an algal bloom within those ponds. Now these animals mean big business, but they also mean big responsibility. They have to be kept healthy, and their waste has to be dealt with. Now, current technologies in this industry rely heavily on the use of settling ponds and waste lagoons. The water from these ponds are many times spread on the surrounding fields, and the solids, and that means the composted hog poop, is amended into the soil in the fields. Thus any compounds used to treat the hogs to maintain their health, such as antibiotics, nutrients, vitamins, any sort of drug, has the potential to enter the environment of eastern North Carolina. Now, let's look at a specific example. One chemical that is used to treat hogs is the antibiotic tetracycline. Tetracycline has a log KOW of 1.3 minus 1.3 to 0.05. And the solid water distribution coefficient, KD, is 300 to 2,000 liters per kilogram. Now the low KOW values indicate that tetracyclines are hydrophilic. Remember, minus 1.3 to 0.05 is the KOW. That means it's more hydrophilic or water-loving, and therefore it's more water-soluble, and it has a lower tendency to bind to the organic carbon. Now this study was published by Aga et al., and they took tetracycline and applied it to the topsoil in 2 areas of the state of Utah. Why they did Utah, I'll never know. They then measured the level of tetracycline in the soil at 7-day intervals. So they just applied it to a patch of soil in Utah and measured the level of tetracycline at 7-day intervals. So we see day 1 where they applied it, day 7, 14, 21, and 28. And here we have 2 different sites. We have a Sandhill site and a Middle Loop River site, or MLR. Okay. They then measured the level of tetracycline in that soil at these 7-day intervals. Now, as you see in this first figure, in figure 1, the level of antibiotic within the first few centimeters of the top of that soil decreases over time. So this is the level on day 1, this is the level on day 7, level on day 14, level on day 21, and the level on day 28. And you see by day 28, by the end of 1 month, this concentration of tetracycline within the first few centimeters of that soil is almost negligible. So it's decreased quite a bit. It's either broken down or it's migrated. Okay. They took sediment cores. So they just took a tube full of sediment. They applied the antibiotic a slurry of hog manure, a slurry of the hog manure containing the antibiotic to the top of this sediment core, and then ran water through it. So they put this slug of hog manure right here, which contains their antibiotic. They pour water through it here, and then they collect fractions out the bottom. And this would essentially give you these fractions. So on day 1 they collected this fraction, day 3, day 4, day 5, so on and so forth. And they did this for 30 days. So they ran the water through this sediment core for 30 days and collected these fractions. And they measured the level of tetracycline in each fraction. In other words, what was coming off of the column on that particular day. And as you can see, the antibiotic moved rapidly through this sediment core, with the bulk of the compound coming off around day 3.5, which is be right here. So it takes about 3.5 days for the tetracycline to move. So what we see here is that this decrease in tetracycline concentration, while it may be due to some breakdown of the material, it's also due to the rapid movement of this antibiotic through the sediments, possibly into the groundwater. This rapidity of movement is directly due to the solubility of the compound and its behavior in water and soil. So that's quite a good example of the movement of toxicants within the environment. Now, because antibiotic residues can enter the environment from the excreta of treated animals or even humans, but in this case treated animals when the manure is spread on the land, we need to know what the fate and transport of these compounds is within the sediments and within the soils. Now, the risk of contaminating the groundwater with antibiotic residues can be minimized or even eliminated by good agricultural practices and management. For example, an appropriate storage period of the manure to allow degradation of the antibiotics before it is applied in soil could reduce environmental contamination. And that's a statement from Aga from his paper. He continued by saying that the influence of soil conditions, the application procedure, whether or not the soil can be plowed or left undisturbed, as well as the intervals of manure application, are also some of the important factors that need to be considered in order to minimize antibiotic exposure of susceptible microorganisms in the soil. So we don't want to get rid of our bacteria and fungi in the soil, because they not only help break down some antibiotics, they also help break down a lot of other contaminants within our environment. Now, before decisions and appropriate actions can be made, excuse me, information on the concentration of antibiotics in the manure would be necessary. So you need to know what these animals are being exposed to and what they're excreting. Excuse me. And so this just shows ground movement of contaminant within our environment. So if you wanted to measure the presence of something in the environment, say we go back to this first picture that we had here, and we wanted to see if there was a contaminant present in this soil, what we could do is take a sediment core. So we just take a round tube and punch it down into the soil, pull it up, you can split it in half and see what it looks like this. And then what this represents, if this is the top of the soil and this is the bottom of the soil here, the top would represent any present day contaminants we might see. And as you go along these sediment cores in this direction here, or if you say down this way, what you're doing is basically going back in time. So in this graphic representation from Battleground Lake in Washington State, we have the present, we have 4,500 years ago, we have 9,500 years ago, 11,000, 15,000, and 20,000 years ago. So you're basically going back in time as you go down this. That's why I said when we looked at this, these were the older sediments down here and these were the newer sediments up here. But what you would do, you would take these sediment cores and you would cut them up into little fractions. So you would take this section and then this section, and then this section, and so on and so forth. And you might not want to go back 20,000 years. You might just take these first few centimeters and break those up into little sections. And what you do, you would then extract them with organic solvents or water or whatever environmental compound that you might be looking for. You would use the appropriate solvent, and then you would run them. And here we see a picture of a liquid chromatographic mass spectrometer. You may use gas chromatography or some other analytical process in order to see what is present within those areas of the sediment core. And so with that, we can use that process to measure the movement of toxicants in the sediments and soils within our environment. Now here we see the profile for 4 separate toxicants. We have DDT, PCB, agricultural or chlordane, and benzoapyrene. In this case, they took sediment cores, fractionated them. Like I said, they took little sections of them, extracted and measured them, and then they looked at for the presence of these different compounds. So if you look at the DDT compound, you see this graph was taken and published on data. The top of the sediment core would represent the year 1995, and then they fractionated it into different areas: 1965, 1935, and 1905. And what they see is that right around 64, 65, there's a spike. In other words, concentration of DDT was highest at the sediment level that would represent that year. So that would be the year we expect to see the highest usage of DDT. And indeed, if you look at these different graphs, the purple represents what they measured. If you look at the red graph right here, that represents the use of DDT in the environment. And the orange or yellowish brown graph here represents the peak production of DDT. So you see they correspond quite well here within the United States. As far as PCB goes, when they measured PCBs, those were about the same time, maybe a little later, maybe 1966 or 1967. We saw a spike in PCB levels in the sediments. And if you look at the sale of PCBs, we see, well, yes, that corresponds with the sale of PCBs. So they were widely used during that time period. And it's reflected in the level of contaminants that are in the soil. And so if we're thinking, okay, 1995, and this is just lower down and represents a larger concentration, these compounds are not degrading. They're still present in those sediments. They're just buried now. And the question is, are they moving farther down? But the movement of them is not something that you would consider to be an explanation, because it's corresponding, this peak in the text is corresponding with the sale. So that's what that is telling you, that it's not moving. It's occurring where the peak activity of use occurred. Now here let's look at chlordane, which is a chlorinated pesticide. And if they measured that in different levels, so let's say different levels, this level versus that level versus that level versus that level, they measured the chlordane in these levels, we see that the peak use was right around 1990 here. Peak concentration was 1990. However, the largest agricultural use was back in, see if this is 65, this might be 75. So between around 1970, we might see the largest agricultural use, and yet we're seeing our spike here right around 1990. So that tells us that the presence of this chlordane was not necessarily related to agricultural use, but probably to some other use within our environment. Perhaps land application in yards for insects, could be termites or something else. Who knows? We would have to go back and look at the different uses of chlordane in our environment. Okay, now for benzoate pyrene. Now benzoate pyrene is a polycyclic aromatic hydrocarbon. And we see here the blue line represents the concentration within the sediment. So we're going from the highest, from the top of the sediment core to the bottom of the sediment core. And we're looking at the different ages, different time periods, excuse me, here. And we see a peak in benzoate pyrene right around 92, 90, 92, somewhere in that range. And so what this is telling us is that if you follow the red graph, that's urban land use. Benzoate pyrene is a combustion byproduct. So you got cars, you got industrial applications, you got a variety of things that can generate benzoate pyrenes. I can't see my arrows, so you guys might be going nuts. Oh, there it is. So what we see is that as in the industrialized and urban land increases, the level of PAHs or benzoate pyrene increases. And so it follows a general trend of urban land use. In other words, less land in agricultural practices and more land in urban uses such as industries. And so those are increasing. And so we could follow this over time, and the pollutant profiles will reflect the current and historical land use and changes in contaminant load over the time periods. So that brings us back to our slide showing the movement of compounds through the environment. So we've seen from our two examples one toxicant that binds tightly to sediment particles and should have a limited bioavailability. That would be the chlorpyrifos. And we also see one that is highly water soluble and moves rapidly through the environment. That would be the tetracycline. But if we consider the movement of toxicants, we have to remember the influence of the changing environment on itself and on the movement of contaminants. In other words, what is the pH of the sediment? How wet is the sediment? How dry is the sediment? Is there a lot of wind being involved? Are there aquifers present? Are there organisms living in that area? And so on and so forth. So we have to consider multiple factors when we consider the movement and fate of contaminants within the environment. Do they absorb to organic matter? Are they volatilized? Are they degraded by UV radiation? Is it being deposited in the water bodies from atmospheric deposition? Does it enter the food chain? Is it biodegradable by fungi and bacteria? Does it undergo chemical degradation when it comes in contact with organic matter? Is it leaching from the sediments into the groundwater? Is it being taken up by trees? Is it being taken up by organisms? Has it occurred as the result of a spill? All of these are factors that need to be considered. Now, what happens when there is a dramatic change in the environment? For instance, a storm such as a hurricane. This can lead to the movement within the environment of even those contaminants that are considered immobile. Now here we see the after effects of one of the many hurricanes that have come through our coastal region. Now you see the sediments flowing into the ocean from the land, and they would be represented here. See these dark brown areas within the river? That's the sediments coming down the rivers and into our estuaries here. And this green bloom is the algal bloom that is being carried out and that shows the movement of nutrients from our land area offshore through our estuaries and offshore. So this algae or green color, in this case we're seeing suspended sediments, these are present due to the forces of the hurricane that caused flooding to the Pamlico, Neuse, Chowan, and Roanoke rivers. And it's just going out into the estuaries and out into the ocean. A more dramatic effect is seen here, where you can actually see the suspended soil particles moving into the sound. So what we see here, if you look to the right of this lower photograph, would be upstream. This would be I think it was the tar Pamlico. And this is the sediment particles coming down and moving into the estuary in this direction. So you see this big front here, like a cloud front, except this on the right is water coming from upriver, carrying large amounts of sediment and moving into our estuaries, where you still see the blue water on the left. So this was after one of the major hurricanes. I think it was Fran, but I won't swear to it. Now, what this storm did was move not only the sediments, but many contaminants around the river and the sounds. Now, where previous contaminants were not present in the water, as you see here with the, this was a junkyard that was in Newbern that got flooded. The contaminants were not present in the river, where they were present on land, but when the river came up and flooded this area, you can see the oil slicks, the oil sheens on this river, where the oil that is present in these cars, either gasoline or motor oil or brake fluid or whatever, transmission fluid, it's being flooded out and moved from here into the water and then will go down the river. Now, in this graph, which we see here on the right, we actually see the different PAHs found in stream sediments. Now, these were measured in South Carolina's areas, not North Carolina, but it occurred at the same time, and therefore it's close enough. And what they did, they measured the levels of PAHs in the forest, urban, and industrial sites of different areas around South Carolina. And it goes from the larger PAHs to the small PAHs as far as chemical structure. So it'll go from the larger PAHs, such as benzoate-pyrene, benzoate-anthracene, and phenanthrene, to the smaller PAHs, such as pyrene and fluoranthene. And it actually shows the decrease in size of the PAHs present. That is, because microbes within the sediment help degrade these high molecular weight compounds and break them into smaller or lower molecular weight constituents, then we see a change from lower levels of the higher molecular weight compounds to higher levels of the lower molecular weight compounds. So we know our microbes are helping break down these products, which are very tightly bound to sediment particles because they're extremely hydrophobic. So what happens if these particles do get into the water? Then we have to consider their potential effect on biologics. For instance, if we wish to examine the movement of toxicants from sediment into water and into fish, we could calculate both the KOC and the bioconcentration factor, or BCF, to help us compare different chemicals and their propensity for bioavailability. In other words, whether or not they can move into a living organism. Now, we could take a sediment core or construct a sediment column and apply the material to the top of that column. We could then run water through the column, and so we take the material, apply it to a sediment column, run water through the top of the column, much like they did the tetracycline experiment, collect those fractions, and then use those fractions to expose fish. And we would then measure the uptake levels of these fish that have been exposed to these fractions and see what their bioconcentration factor is. That would tell us whether or not the particles are smaller, larger, and how hydrophobic or hydrophilic they are. Now, this whole process is exactly what was done by some researchers to compare some different PAHs. Now, I want you to note this is a study. It was published in the Journal of Environmental Toxicology and Chemistry back in 2007, and they applied some material to a sediment column, collected the fractions, and then measured the different PAHs that came off of that column. And so here we see the different PAHs. We have naphthalene, acetylnaphthalene, fluorine, phenanthrene, anthracene, pyrene, benzanthracene, benzoate-pyrene, which you've seen the structure for, and this sigma PAHs is just your total PAHs. And so what they did next, they calculated the KOWs for each of these compounds, which tells you and gives you an indication of the hydrophobicity of these compounds. They then looked at the water solubility, how much of these compounds was dissolved within the water. And so we see that the smaller compounds, such as the naphthalene, are more highly water soluble than the larger compounds, such as benzoate, which is very water insoluble. Excuse me. And so they measured this for each of these fractions or each of these compounds. They then looked at exposed fish and oysters to this and looked at the concentrations of these compounds within the fish and within the oysters. So we have the fish concentration study and the oyster concentration study. And if you look at this, in this earlier study here, the naphthalene was taken up more than some of the other compounds. But when you look at the present day, that was a previous study that had been done. When you look at the present day study, you see that these compounds are being taken up in fairly decent or similar concentrations. Whereas if you look at oysters, we see that oysters take up less naphthalene. And what they're probably doing is taking it up, but they're also getting rid of it at a similar level. And then you have the uptake of some of the other compounds such as fluorine and phenanthrene and anthracene. And then you have take up of these the higher molecular weights. And that's because these compounds are more lipophilic, and so therefore you're seeing more of them in the lipid-rich tissues of these organisms. And so using this data, you calculate the log concentration factor, which is also the bioconcentration factor, or BCF. And so that's how you're able to calculate that. And just so you know, the SPMDs are semi-permeable membrane devices, and those are used to model uptake in oysters and in fish. And now with that, I'd like to thank you for listening. I hope you have a good evening, a good day, and we'll talk again later. Thanks.